the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are currently going through orthogonality and least squares problems. This specific topic and series of videos that we're going to go through is for the Gram-Schmidt process, which is an awesome process for orthogonalizing bases. And that's what I say right here. We're going to turn our attention to producing orthogonal and orthonormal bases for subspaces of Rn. And as a reminder, part of our task in previous material was to rewrite a given vector y as the sum of two vectors. And by the way, that y is in some vector space V. Now, those two vectors satisfy the following conditions. One has to be the projection of y onto the subspace spanned by some vector u, and the other was a vector orthogonal to that projection. I was calling that the projection of y onto w perp, and then the vector, which was the projection of y onto the subspace spanned by a vector u, I was calling that the projection of y onto w. However, that notation's not really super useful for what we're going to be doing here, so I'm going to adjust that notation right now, in fact. So suppose that we were given some vector u sub 1, and we wanted to find the shadow of y onto the subspace created by that vector u sub 1. Well, the nice notation for that, honestly, in my opinion, would be this right here. Notice I'm not using vector notation on that u sub 1. That is intended purposefully so that we know that that stands for the subspace spanned by the vector u sub 1. And the rest of that is just the projection of y onto the subspace that's orthogonal to the subspace spanned by u sub 1. And again, y is just the sum of those two vectors. But now we're going to grow that definition or that theorem a little bit more, because what if the subspace, which they're calling w but I'm calling u sub 1, what if that subspace was not a single dimensional subspace? In fact, what if we were to say that w was the subspace, for example, spanned by the vectors u1 and u2? So let's pretend for a moment that u1, u2, and u3 are these vectors right here, and let's pretend again that they're orthogonal to each other. Then the axes u1, u2, u3, which are not vectors, they're actually just spaces. Well, those are the subspaces actually spanned by, respectively, the vector u1, the vector u2, and the vector u3. Obviously they go in the other directions here, but my intent is only to draw another vector that's in the first octant. So there's my vector y in the very first octant. It doesn't have to be in the first octant, I'm just doing that right now. What this statement here is telling us is that that vector y can be written as the projection of y onto the subspace spanned by u1 and u2, plus the projection of y onto the subspace spanned by a vector orthogonal to the subspace u1, u2. In fact, let me write it that way. So my notation here is telling us that this is the shadow of y onto the subspace spanned by the vectors u1 and u2, and this over here is a projection of y onto the subspace that is orthogonal to the subspace spanned by the vectors u1 and u2. Let's go ahead and visualize this. All right, so what you see right here is the vector y in blue. Its shadow onto the plane spanned by the vectors u1 and u2 is shown right here. That's actually what that gray vector is. Now I want to write y as the sum of two vectors. Well, as we've said right here, y is the projection of y onto the span of u1 and u2 plus the projection of y onto the space orthogonal to that, and in this three-dimensional example, the projection of y onto the space perpendicular or orthogonal to that plane is going to be this green vector right here. And you can see that that vector, if you add it to the projection of y onto the space spanned by u1 and u2, you will get the vector y from tail to head addition for vectors, geometric addition right there. So you can see it does work out. I'm going to move it back because technically I'm also moving the vector u sub 3. But that shadow cast into the perpendicular space, or the orthogonal space, that is actually called the projection of y onto the space orthogonal to u sub 1-2. That's how I'm going to call it because, well, it is technically orthogonal to the space spanned by the vectors u sub 1 and u sub 2. And that's the idea here, that all vectors can be rewritten this way. And I want to show you a visualization of this right now. It's somebody else's visualization, but I think it's really cool. And as you can see right here, this is actually a demonstration of what's called the Gram-Schmidt process. So we're going to illustrate what we're going to be doing in this video, the concept of the Gram-Schmidt process. You're given a set of vectors. You can kind of see them right here. And I'm going to try my best to manipulate this. It's really hard for me to manipulate because I'm using 2 fingers on a screen and it's a little bit weird and wonky this way. Maybe I'll try it like this with a mouse. Anyhow, notice you have 3 vectors right there. The Gram-Schmidt process is going to orthogonalize those vectors. What we're going to do is choose one of them to be kind of the central vector that we're going to keep in place. And then the other 2 vectors we're going to orthogonalize based upon that single vector. But if you take a look at those letterings, w sub 1 is that red vector right there. So we're going to choose our kind of anchor vector to be that w sub 1, and we're going to make everything orthogonal to that vector. So notice I've just turned that vector black because what I'm stating to you right now is that'll be our anchor, and then we're going to force those other vectors to be orthogonal to that vector. Now we've just said that every single vector is the sum of the projection of that vector onto a space spanned by 1 or more vectors, and the projection of that vector onto a space orthogonal to that subspace. So if you think about it, this vector right here, w2, if you take its orthogonal projection onto v sub 1, we can actually create its projection onto a component space or a perpendicular or orthogonal space to that. So again, imagine I'm taking this w sub 2 here and I'm creating a shadow onto the subspace spanned by v sub 1. Well, when I get that shadow, I happen to know then that that w sub 2 can be written as the sum of that shadow and the shadow of a vector orthogonal to that. And in fact, that vector is this guy right here. You can see those 2 black vectors are actually perpendicular to each other. And if I turn on the plane that they exist on, it's really hard to see here, but let's see if we could do it. So there's our original vector, v sub 1. We were really interested in this w sub 2, this green vector. And what we did is we took the shadow of it onto v sub 1 so that we could find the orthogonal vector to that. Now, if I turn off w sub 2, you can see that we have 2 orthogonal vectors building this plane here. Now notice that blue vector is actually not on that plane. But what I'm going to do is take the shadow of that blue vector and I'm going to project it onto that plane. It'll create a nice little shadow right here. And getting that shadow, I'll be able to find the vector perpendicular to that shadow. And that would be that vector right there. And notice when doing this, you now have 3 orthogonal vectors created from 3 non-orthogonal vectors. And it was done using the formula that we've just talked about, which is this formula right here. Now, to be honest, that's a lot to absorb and really kind of hard to visualize. That's why I had that illustration of the Gram-Schmidt process applet open on GeoGebra. So let me show you the process. It's actually pretty simple, but let's go ahead and go through the process anyway. For the following process, I'm going to use a different notation than likely your instructor or the author of your textbook uses. I'm going to use the notation v sub 1 through k to denote the subspace in Rn spanned by the orthogonal vectors v sub 1 all the way through v sub k. So this subspace right here is actually spanned by v sub 1 ... all the way through v sub k. And that notation works very well if you keep things in order. The only one it doesn't actually work well for is if you have a space just spanned by the vector v sub 1. Well, then I will call that v sub 1. So the space spanned by the vector v sub 1 is actually just going to be v sub 1. I will continually repeat that when I go through this. So let's go ahead and talk about this how-to. Given a basis x sub 1 through x sub p for a subspace W of Rn, our goal is to create an orthogonal basis for W. Now, if that picture didn't help you out, hopefully this will. You're going to choose one of those vectors, and generally we just choose the first one in that basis. By the way, this basis, these vectors are not necessarily orthogonal. We're going to force them to be orthogonal, or actually we're going to transition them into orthogonal vectors. So you're going to choose one of them to be kind of the anchor. So I will just say let v sub 1, the vector, equal the first vector in that list. Again, it doesn't really matter which vector you choose, but we're choosing v sub 1 to equal that vector. Now, before I go to step 2, I want to convince you of something. If x sub 2 is not in the subspace spanned by x sub 1, which is the same thing as v sub 1, then x sub 2 must be the sum of these two projection vectors. The sum of the projection of x sub 2 on the space spanned by v sub 1 plus the projection of x sub 2 on the space spanned by v sub 1 perp, or a vector perpendicular to v sub 1. However, if you subtract the projection of x sub 2 onto the space spanned by the vector v sub 1 from both sides, you get the following. Now that's simple arithmetic, or actually algebra technically, but what this gives us is the actual perpendicular vector, or in other words, the orthogonal vector. So we know the vector orthogonal to this projection vector right here is going to be the projection of x sub 2 onto v sub 1 perp. And that vector is just x sub 2 minus the projection of x sub 2 onto v sub 1. Notice that's exactly what I have right here. But notice this does not say the projection of x sub 2 onto v sub 1 perp. Why? Well, I can tell you why. Because I'm letting the vector v sub 2, which we did not have before this very moment, I'm letting v sub 2 be that orthogonal vector. So v sub 2 will be orthogonal to v sub 1. Remember, the projection of x sub 2 onto v sub 1 perp is a subspace spanned by all vectors perpendicular to the vector v sub 1. So therefore, v sub 2 is a vector perpendicular to v sub 1. So if we make that definition right there, we now get a second vector. We have v sub 1 that we called x sub 1, and we get v sub 2, which is a vector perpendicular to that, which is exactly what we want. Now, I'm not going to leave this notation in here because, well, that's not normally how people remember it, but really, the projection of x sub 2 onto the vector space spanned by the vector v sub 1 is this right here. And you should know that from our previous work in this course. So v sub 2 is x sub 2 minus the projection of x sub 2 on the vector space spanned by v sub 1. Great, so we have two orthogonal vectors so far, built from our first two vectors in our set that we were handed. Well, let's go to the third vector in that set. Now here's the deal. When I build my third vector, I not only need that vector to be orthogonal to v sub 1, I also need it to be orthogonal to v sub 2. And that's why I have this notation here. Again, if you go back to this statement right here, I could trade out x sub 2 for x sub 3, and I could say, great, well, x sub 3 is a projection of x sub 3 onto the space spanned by v1 and v2, plus the projection of x sub 3 onto the space v1 through v2 perp. This guarantees that x sub 3 is the sum of two vectors, one which lies in the space spanned by the vectors v1 and v2, and another perpendicular or orthogonal to that space. And by our previous work right over here, if we subtract the projection of x sub 3 onto the vector space v sub 1 through 2 from both sides, we get that our projection of x sub 3 onto the v sub 1, 2 perp becomes this difference between x sub 3 and the projection of x sub 3 onto v1, 2, and we're going to call that v sub 3. Remember, v sub 3 now is perpendicular to the subspace spanned by vectors v1 and v2. That is, we've just created a brand new vector that's orthogonal to both v1 and v2. So we have v1, we've created v2, which is orthogonal to v1, and we've created v3, which is orthogonal to both the spaces spanned by v1 and v2, and you continue this process on and on and on, each time subtracting the projection of your vector x sub whatever onto the space v1 through v sub whatever minus 1. So here's where the general formula comes in. We're going to let v sub p, our last orthogonal vector, or our pth orthogonal vector, be equal to x sub p minus a projection of x sub p onto the vector space that's spanned by v1 through v sub p minus 1. That is going to be this messy looking mess right there. Essentially all you're doing is you're taking your current vector x sub p and subtracting off all the orthogonal projections you previously found. And that's a great way to think about it. You start with your kind of anchor vector. Your second vector, well, you take x sub 2, the second vector in your given set, and you subtract off the orthogonal projection onto that v sub 1. Your third vector, you're going to take your third vector from your set, you'll subtract off the orthogonal projection of that third vector onto v sub 1, and subtract off the orthogonal projection of that third vector onto the vector space spanned by v sub 2, and so on and so forth. So each time you go down the list, you just keep another subtraction going. And this process is called the Gram-Schmidt process. The set v1 through vp that is formed from the previous process is an orthogonal basis for our subspace that we were working with. Moreover, and this is kind of the important or an important part, it is actually very important, the span of v sub 1 through v sub k is the same as the span of x sub 1 through x sub k for every single k from 1 through p. That is, the span of x1 just by itself. Let's just look at the span of x1. Well, that should be the same as the span of v1. Well, that makes sense because x1 and v1 were actually the same vectors. But this is saying the span of x1, x2 should be the span of v1, v2 as well. And I hope that makes sense because if you take a look at this picture right here, our original vectors were w1 and w2. And then what we did is we created v1 and v2 based off of those. But let's just take a look at the span of w1 and w2 right now. That plane right there is actually the span of w1 and w2. It's kind of hard to see on this applet, but it is. I promise you that is actually the span. You can kind of see it right here. That's the span of w1, w2. However, we adjusted w1 and w2 to create orthogonal versions called v1 and v2. Notice these are orthogonal to each other. They're kind of hard to see again. However, notice they actually span that very same space. Now that's not a proof, but it is a great justification. So let's go ahead and consider this set of 4 vectors right here. And we're going to do a lot of work in this problem. I think that this is such an important concept. The Gram-Schmidt process is not a throwaway process you'll never use again. It is actually a very important process. So we're going to start by proving that this set of vectors forms a basis for R4. There's a lot of ways we know how to do that now in a linear algebra course. However, the way I'm going to show it is just to show that the determinant of this matrix is non-zero, so that I know this matrix is invertible. Therefore, by the invertible matrix theorem, its columns span R4. And I almost made myself a little nervous there as I did it. I forgot to subtract off this negative. Man, that would have been terrible, right? Plus, minus. Don't forget about that. Yeah, so the determinant is non-zero, so the columns of that matrix must span R4. We have proven that. We're done with that. Now we're going to show that this set of vectors is not an orthogonal set. And probably the easiest way to do that is just to choose two of the vectors and take their dot product to show it's non-zero. And you could just take this vector here, which I'll call u sub 1, I'll call this u sub 2, u sub 3, and u sub 4, and you can see the dot product of u1 and u2 is going to be -2, which is non-zero. Therefore, we found two vectors within that set of vectors that are not orthogonal to one another. Therefore, this is not an orthogonal set of vectors. That's all we need to do. Now we're going to use the Gram-Schmidt process to construct an orthogonal basis for R4 using the vectors above. So let's go ahead and enumerate our process. Step 1, choose one of those vectors to be your anchor vector. Well, I'm just going to choose u sub 1 to be my anchor vector here. And now what we're going to do is we're going to build v sub 2. Now remember, we want v sub 2 to be orthogonal to v sub 1. How are you going to do that? Well, we're going to let v sub 2 be the vector that's the shadow of x sub 2 on the vector space spanned by v sub 1 perp. That will guarantee that v sub 2 is perpendicular to v sub 1. And we know that's going to be x sub 2 minus the projection of x sub 2 onto that vector space spanned by v sub 1. Remember, that's the orthogonal projection of x sub 2 onto the vector space spanned by v sub 1 right there. And we're subtracting that off, so we're getting a perpendicular or orthogonal vector to x sub 2 from that. Let's compute this out. X sub 2 is 1, -1, 0, 0. And then v1 dotted with x sub 2. Okay, well, we have x sub 2 right here and v1 right there. So let's go ahead and take that dot product. Pretty easy. You can see it's going to be, let's see, 0 plus a -2 plus 0, 0, divided by v1, which is this guy again, dotted with itself. That's going to be 4 plus 1, or 5. And then we're going to multiply that by the vector v sub 1. And of course, you do have to clean this up because you're going to use it in the next step. There we go. We have our v sub 2. You can dot v sub 2 against v sub 1 and see actually those two vectors are going to be orthogonal. It's 0 minus 2/5 plus 2/5 plus 0. That's going to be 0. So far so good. Let's go ahead and go to the next step here. We want our v sub 3 to be perpendicular to the space spanned by v sub 1 and v sub 2. Let me go ahead and say that again. We want v sub 3 to be perpendicular to the space spanned by v sub 1 and v sub 2. In fact, we want it to be perpendicular to the shadow of x sub 3 onto the subspace spanned by v sub 1 and v sub 2. And that's just going to look like this. You start with x sub 3 and then you subtract off the orthogonal projections onto each of those individual subspaces of x sub 3. So let's see, we have x sub 3 minus the shadow of x sub 3 onto v sub 1 minus the shadow of x sub 3 onto the vector space spanned by v sub 2. And we have to do all this mathematics. So it is actually a little bit of a computational, not nightmare, but it's just a lot of computation in here. X sub 3, which by the way, I'm using x and above I had u. I apologize. I just didn't realize I did that. But anyway, u sub 3 then, but we're calling it x sub 3, is 1, 2, 0, -1. Again, I'm using x sub 3. I should have been using u's here. Maybe I'll change them all really quickly. That was my fault. I was just looking back at the method and copying the x values instead of the u values that we're currently using. Anyway, no biggie. All right, so we have u sub 3. Sorry about that. And now we're going to subtract off u sub 3 dotted with v sub 1 over v sub 1 dotted with itself. Luckily, we already know what v sub 1 dotted with itself is, so that's okay. And v sub 1 dotted with u sub 3, again, v sub 1's right here, u sub 3 is right there. That's 0 plus 4 plus 0 plus 0. We're going to multiply that by v sub 1. Now we'll do the second subtraction. we'll take u sub 3 again, and we're going to dot it with v sub 2. Now the mathematics gets a little bit ugly because we have fractions involved. Well, you can't help that, honestly, but u sub 3 dotted with v sub 2, that's going to be 1 minus 2/5 plus 0 plus 0, which is 3/5. And now we'll take v sub 2 and dot it with itself. And again, this is going to be a little bit of a mess. That's going to be 1 plus 1/25 plus 4/25. That reduces down to 6/5, I promise you. And again, multiply that by v sub 2. Now all we need to do is some arithmetic, which is actually kind of heavy arithmetic here, but not too terrible. Notice that I change everything to additions. I don't have to, and you don't have to. I'm just choosing to do that here. The good news here is that the vectors aren't too terrible. They're not great, but they're not terrible either. And let's go ahead and do the last one here. Again, I'm not going to actually write this part down, but v sub 4 is going to be the projection of u sub 4 onto the space perpendicular to the space spanned by v1 through v3. So how do you get that? Well, you take u sub 4 and you subtract off all those projections of u4 onto the individual spaces spanned by the vectors v1, v2, and v3 respectively. Now, you probably could imagine the mathematics can get very heavy when you do this over and over again for a 5x5 or something like that. However, I'm doing kind of a larger group of vectors right now just to illustrate the process. Rather than doing two different examples, I'm just doing one massive example. U sub 4 is 1, 0, 0, 1. And now we'll do U sub 4 dotted with V sub 1. That'll be 0 plus 0 plus 0 plus 0. Oh, that's kind of interesting. That happened because those specific two vectors are actually already orthogonal to one another. So U4 and V1 are actually already orthogonal to each other. No biggie, just makes the math easy on that one. Now we're going to subtract off the next fraction, U4 dotted with V2. So that's 1 plus 0 plus 0 plus 0. Oh, that's super nice, right? Over V2 dotted with itself, and we happen to have that right here, which is 6/5. We're going to multiply that by the vector V sub 2, which is 1, -1/5, 2/5, and 0. Finally, U4 dotted with V3. Well, that's going to be 1/2 plus 0 plus 0 minus 1. And we're going to write that over V3 dotted with itself. That's 1/4 plus 1/4 plus 1 plus 1, which is 5/2, and then we're going to multiply that by V sub 3. Now, barring any arithmetic mistakes, we'll go ahead and go forward on this one. And you get down to this point right here. Now, there's a lot of room for arithmetic mistakes in here. In fact, you wouldn't know it, but I spent quite some time trying to find an arithmetic mistake I made somewhere, and it was right at the very end, which is super annoying. So be very careful about that. I actually rewrote all these vectors up here. They are orthogonal. You can just double check that if you want. Multiply each of them against, or not multiply, take the dot product of each against each other. You'll find out all the dot products are 0. So we have successfully constructed an orthogonal basis for R4 using these vectors up above right here. The last part asks us to construct an orthonormal basis. Well, that just means normalize these vectors. So that would just require us to divide each vector by the norm of that vector. I'm going to go ahead and quickly write down the norms of the vectors above, and then I'll go ahead and divide each vector by their norms. Now, this is an annoyance, and if you're asked to do this, you should only normalize at the very end. Otherwise, you're going to have radicals all over the place. That last one has a terrible norming factor, but we'll go ahead and sort of write these as their normed versions. I'll write this in green. The first vector I will actually write as its normed version. That wasn't too bad. The second one I'll multiply. Oops, and before I do that, this is actually a square root of 6 over 5, not 1 over 5. So let's go ahead and do that. We're going to multiply each of those by root 5 over 6. And this time, I'm actually going to leave the norming factor outside of the vector. It's just cleaner to do it that way. And I barely was able to fit that in there. Notice I really did a lazy job here with the square roots. I could have brought those in there, but man, it's nasty enough when you have 4 vectors like this. But you can see it is a bit of a process. It's very mechanical, but the process is important. The Gram-Schmidt process that we're using here to orthogonalize a basis is incredibly important and very, very useful. I think that pretty much does it for this video. I hope to see you in future videos. I hope this video was helpful as well. And I hope you have a wonderful day. Be a great human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.